Hello everyone, let's solve some Leetcode today. So today we have Leetcode 33, that is search in a rotated sorted array. This problem can greatly help you to understand what is modified binary search algorithm. So in this problem, we have been given a nums array that is going to be rotated in some way, and then we have to find the given target in that nums array. So a normal sorted array will look like this. We have the minimum number here, the maximum number here. But here we will get a rotated array at an unknown index. Okay. So suppose that I want to rotate this array at this particular index. So I want to rotate this array on the index 2 somehow. So how can we do this, right? Well, we can take this entire part and place it first here. Okay. 4 and then 5. And then we can take this entire part and place it after this. So we will have 1, 2, and 3. That's what a rotated sorted array is. We have rotated this array at the index 2. And then we will have a target from the question that we need to find in this rotated sorted array. What this means is that if target equals to 1, then I need to find out where 1 is in this particular sorted array, and then I will have to return the index. Now understand that indices have also been reset now. What this means is that earlier 4 was actually at third index, right? But in this new sorted array, we are going to consider indices like this: 0, 1, 2, 3, and 4. Indices are still in the same order as they were. Only elements have changed their order, that's all. So suppose that we have an array like this. Here we have elements from 0 to 7, and we have rotated this particular array after the third element. That's why we have 4, 5, 6, and 7 here, and then we have 0, 1, 2, and 3. Now let us try to visualize this particular array or this particular situation with the help of a graph. So usually the graph of a sorted array will look like this. We will start from the minimum element 0 and we will reach the maximum element 7. But in case of our rotated sorted array, it will look something like this. So we will have the same graph again, but this time we have to rotate the entire graph after the element 3. So here in this original graph, the 3 element was here, right? This is the third point, and now we have to rotate around this. So it means that we have to take this entire part, and we have to place it first, and then only we can place this entire part. What this means is that we will have something like this. We will have a third point here, and then the entire rest of the graph will look like this. It will be here. So we are starting from 3 to 7. Okay. And then we will have a break, because now we are going to go for the another part of the sorted array that is going to start from the 0th position to the third position. And this is how you can visualize this situation. You have two parts. You have two properly sorted parts. One sorted part is this, another sorted part is this. So we need to figure out some way with the help of this visualization to create the binary search algorithm that will help us to find out any element inside of this array. The reason we are using binary search algorithm is because it is strictly told in the question to use order of log and solution. And mostly when you're talking about log and solutions, you can only use in most of the questions binary search. So now that we are using a binary search, we know that we will have to modify it also. So let us try to figure out a few rules that we can use to actually create a modified binary search algorithm. So let us try to figure out a few rules. First of all, we know that there are two parts of this sorted array, right? We have this part, first sorted array part, and then we have second part. Now, when we are trying to run the algorithm, we will have a mid pointer. Okay, we will calculate mid pointer. We will have left pointer here. We will have right pointer here, and then we will try to calculate a mid pointer in the binary search, right? Now, suppose that the mid pointer actually is here. Now, how do I know whether this mid pointer is in this part of the array or in this part of the array? How do I know this? In which part are we present currently? Because that is one of the first things that we should know, in which part of the array we are present. So if we notice properly, we will see that we are on 7th element in the array. Now, in order to find out in which part we are, we can try to compare this 7th element with the element at L index, okay, left index. So right now the element at left index is 4. Since this particular element 7 is greater than the 4, that is the smallest element on the left side, we know that we are on the left side of the sorted array. But in case if our mid pointer was actually on this place, that is the first element, and we will try to compare the 1 with this particular element L, we will see that the 1 is smaller than this one. It means we are on the second sorted array. So we have our first rule right here. If the element at mid index is greater than or equal to the element at the left index, this index, then we are on the left side of the rotated sorted array. Otherwise, else we are on the right side of the rotated sorted array. Simple, right? Now suppose that our mid pointer is right here on the 7th index, that is on the first sorted array, and now we want to find out our target. So in case the target is less than 7, the current mid element, then the target can be 4, 5, 6 or 1, 2, 3 because all these elements are less than 7. Now, how do we know whether we need to search in this part or in this part? That's a big question, right? So what we can do is after comparing our target with the element at mid, that is 7, we can compare it with this element, the element at L index. And if our target is smaller than this element, we know that it will have to be in this side of the array. So in this case, we will know that none of these elements 4, 5, 6, 7 are going to be our target, and we will shift our left pointer to this place, mid plus 1. So this gives us our second condition. So if our target is greater than or equal to the element at left index, but it is less than the element at mid index, then we can say that we need to shift the R pointer from here to this place. Why? Because our element will be somewhere here. It is greater than the 4 and less than the 7. But in any other case, we know that it will be on this side of the array, and that's why we are taking the L pointer and shifting it right here. And so in the else, we have L is equals to M plus 1. Now suppose that the mid pointer is right here in the second sorted array. Now how can we find out our target? Well, if the target element is less than 1, we know that it has to be in this direction. Why? Because it is a sorted array, right? If it is less than 1, it needs to be in this direction only, because every element in this direction is going to be greater than 1 for sure, because we are in the second sorted array. So if the element is less than 1, it is very simple. We will take the R and we will place it right here in this index, and the L will stay at the same place. But if it is not less than 1, then we have 2, 3, 4, 5, 6 and 7 as potential answers, right? It means our answer can be in this part or in this part, right? How do we know in which part we need to search? Because we cannot go in both the ways in binary search. So to figure that out, after we have compared the target with 1, we will compare it with the 3. 3 is the element where R will be present, and it is the maximum element on this side. So if the target is greater than this 3 also, then we know that we have to come back here 4, 5, 6 or 7. It means we will have to search in this part of the array. But if it is not greater than 3, if it is less than 3, we know that we have to search right here in this part only. So with this observation, we have another condition that we can use in our binary search algorithm. So the third condition is very simple. If the target is greater than the nums of mid index and it is less than or equal to the right index, we know that the target is somewhere between mid index and the right index. So we will simply take the L and make it mid plus 1. But in any other condition, we know that the target is going to be in the left side of our array. So we will simply take the right pointer and we will shift it to mid minus 1. Now we have three conditions, right? Well, there is one more thing to notice. This particular condition is only valid when we are on the left part of the rotated sorted array, and this is only valid when we are on the right part. So that means we have to use these conditions 2 and 3 based on the first condition, whether we are on left part or we are on right part. So now we have all the three conditions. We need to create a modified binary search algorithm. So now let's go ahead and look at the code. Now let us look at the code. First of all, we are initializing the left pointer with 0. Then we are initializing the right pointer with the ending index of the nums array. And now here we have our binary search loop. So we are going to run the while loop on the left less than R condition. In case the left ever becomes greater than the R index, that means we can stop the loop because we have gone through the entire array. Now here we are calculating the mid index. Then we are checking if the element at mid index is actually the target. If it is target, then we immediately return the M because M will be the answer. Then in this condition, we are checking if the element at the left index is less than equal to the element at the mid index. If that is the case, then we are in the first part of the rotated sorted array, and we are going to use the second condition that we discussed to figure out the target. And here we are checking if the target is greater than equal to the element at left index, but it is less than the element at mid index, then we are going to shift the R to mid minus 1. Otherwise, L will be shifted to mid plus 1. Else, we know that we are on the second part of the rotated sorted array, and so we are going to use a third condition to find the target. So here, if the target is greater than the element at mid index, but it is less than equal to the element at right index, we can simply shift L to mid plus 1. Otherwise, R will be shifted to mid minus 1. And once this entire loop is done and we have not returned the answer using this condition, it means we need to check the element at L index. So if the element at L index after this entire loop is done is equal to target, then we will simply return the L index. Otherwise, we will return the negative 1. And this will happen when the L and R become same, or the R will cross the L right before we find the element. So in that case, L will be at the correct element, and we have to check if the element at L is basically equal to the target. If it is, then return the L index, otherwise return negative 1. So now let us run it and see what happens. So yeah, our solution runs in 0 milliseconds, it passes 196 test cases and beats 100% solutions on Leetcode. This number is questionable, don't trust it, but yeah, it's a pretty efficient solution because we are using binary search. So now let us try to look at the space and time complexity for this particular solution. So the space complexity is going to be constant because all we are doing is having L and R and mid pointer, and these are going to take the constant amount of space no matter what is the size of our array. So the input array can contain 1 million elements, but the space taken by L, R and M is going to be constant no matter what the size of the array is, and that's why it is going to be fixed, and that's why we have order of 1 space complexity. The time complexity is order of log n because we are using binary search to divide the search space by 2 each time. And that is why we will have log n time complexity. Just let me know in the comments. Now we will meet in the next video. Till then, bye.